All right, folks, good morning. Please, we are waiting for a couple of people to join, then we'll kickstart.
Okay, Doc.
Right, thank you. I hope you guys are doing very well.
By His grace, Doc. What about you?
I'm doing well by God's grace. Thank you.
Yes, sir. Good morning, sir.
Okay. Think about 30 people are in. One more person to join, then we'll kickstart. Folks are too late in this morning lecture. Okay, I think we will start. We can't be waiting forever. Ajaman, are you here?
Yes, I'm around.
Okay, all right. I think we need to start because we are expecting about 50 people and only 30 people. 29 are in, so maybe we just get 30 and then we start. Because we can't let folks wait and wait and wait.
All right, sir.
Okay. Okay, I think we will start. We'll kickstart because about 30 people are in. Okay, so let's start from here. So last week we were able to talk about the pressure, the osmotic pressure, and then the diffusion pressure deficit. And then we say that when we come to the osmotic pressure here, what is determined by the what? Is determined by the amount of solutes in the solution. It's affected by the temperature, okay, the concentration, okay, all right, and then hydration of the molecule is how the water actually breaks the solute molecules in the solution. So basically, this is what is here. Okay, the terms here, these are what affect osmotic pressure. Osmotic pressure is pressure due to what? Due to the amount of what? Due to the solute in the solution. And it is governed by the what? It is governed by the concentration, the ionization of the solute, the temperature, and even the hydration. The hydration talks about how the water molecules is going to dissolve the solute. And then after that, we move on to the two main, this very important formula here. And we made mention that the diffusion pressure deficit is equal to osmotic pressure minus the table pressure. You remember the table pressure is the pressure as a result of the what? The wall, all right? And then we have the osmotic pressure as a result of solute. So the two of them actually operate to give the pressure deficit. And the pressure deficit is the sucking pressure or the suction pressure. What the solution uses to draw water onto itself by the process of osmosis. So this is what we ended the last time. That diffusion pressure deficit, which is the same as the word, the sucking pressure or the suction pressure. The sucking pressure or the suction pressure is what draws the water to the solution. And that's what we ended our class. So, and then we went to something we call the water potential, which was last time I was rushing through. So the water potential, when we talk of the water potential, it is basically the tendency of water molecules to move in a system. Like, so water moving from one point to another is what we term as the what? The water potential. The tendency of water to move. So when it comes to the tendency of water to move, it is measured in what? As a kilopascal. Kilopascal, yeah, that's where it's measured. So when I have two regions, okay, the tendency of water moving is what we term as what? What is termed as water potential. All right, and then pure water has the highest water potential, and this high water potential is what? Is zero. Okay, the tendency of water to move from one point to another is what we term as what? Water potential. It's the tendency that water will move from one point to another. Okay, it's so like the tendency of water to move from a region of what? Dilute solution to concentrated solution is what we describe as what? What we describe as water potential. All right. And then we made mention that, so when you have the water potential, the one that is more negative, if you have more negative, it means you have very low water potential. And if you have what? If you are less negative, you have high water potential as usual. So solution has what? Because of the what? Because of the solute in it. So when you anytime you put solute into water, okay, it lowers its water potential. Okay, so because of that, pure water has higher water potential than solution. So when you have pure water there in solution, the water will move from where there's pure water to where the solution is. All right. So then we ended our class with this one, with this diagram of me asking that where will the water move? And clearly you can see that here the water potential here is higher than the water potential here. And so water will move from the -100 to the -500. The reason being that this the -100 contains more water than -500. So -500 is a concentrated solution due to the presence of solutes, and then -100 is dilute solution. That is why the water potential there is high. Now, today we're going to talk about solute potential. So the solute potential, as I explained earlier on, so the solute potential is actually describing basically the amount of solute in the solution. And if you look at my diagram here, this diagram I have here, okay, this diagram I have here, okay. Now, you can see one thing. You see all these things here, let's take it. So these are free water molecules. These are free water molecules. The red one, let me do the size of it. Oh. So you can see these ones here are the free water molecules. The red. These are the free water molecules. And then this what the brown, the big brown stuff are the what? Are the solute molecules. Now, if we look at these two here, what can we see? You see the free water molecules. If you have solute in the solution, the water molecules here get attached to the what? To the solute. And so their movement, they are not really free to move because some of them tend to bind to the what? The water molecules tend to bind to the solute. All right, let me take it again. So remember the previous one, I said that what? I said that if you come here, the water potential, that solution has lower water potential. Why is solution having lower water potential? This is because when you have solute in the solution, the water molecules tend to bind themselves onto the solute. So because of that, the solutes are not what? The solutes are not allowing more water molecules to move. Because you see, if you look at this brown thing here, you can see a number of water molecules attached to them. Okay, so because of that, because of the binding of the water molecules, okay, the binding of the water molecules to the what? To the solute, the number of free water molecules to move, they are not many. All right, so having solute in the solution actually what reduces the water potential. All right, so which means that we have water potential, we have the solute in the solution contributing to the what? The water potential. Okay, so we have the solute potential like this here. This is my solute potential, and this solute potential is coming from the fact that the solute is dissolved in the water. Okay, so the greater the amount of solute in the water, the what? The lower the what? The water potential. Why? Because when you have a lot of please mute your mic. Please mute your mic. Please mute your mic. Please mute your mic. So when we have a lot of what? Solute. Let's say we have a lot of salt in the solution. What is going to happen is that more of the
Patrick, please mute mic.
More of the water solvent, okay, molecules are going to bind to the solute. And when they bind to the solute, they will reduce the free water molecules. And so anytime we have a lot of solute in the solution, it reduces the water potential. All right. So because of that, okay, water potential, that's what solute molecules tend to do is that they reduce the number of free water molecules to diffuse. Okay, so you can see from here, my brown stuff has has a number of water molecules attached to them. And so because of that, the number of free water molecules to move tend to reduce, okay, thereby lowering the water potential. So we say that always the solute potential is always negative. Solute potential is always negative. All right, good. So we have another one. So that is the solute potential. Then we have another one. Okay, we have another. So water potential create as a result of, we have another one we call the pressure potential. Pressure
Hello, sir.
potential.
Hello, sir.
Yes,
Sir, please, a minute. Mr. Patrick, can you please mute your mic and then your video? It is distracting, please. Mike, if you can, Patrick, if you can hear us, mute your mic and your video, and you can be working and listening at the same time. Thank you. Sir, you can continue.
All right, thank you. So we have the what? We have the pressure potential. Pressure potential is the pressure you apply to the solution. The pressure you apply to the solution. So we have what? We have something we call water potential. Water potential. So all these potential here. So water potential is basically the pressure as a result of what? Water moving. Okay, the tendency of water to move. And this tendency of water to move, there are two things that we look at. We have solute potential and we have pressure potential. The pressure potential is the pressure you will apply to the what? To the solution. Pressure you apply to the solution. If you remember, it's that when I talk about the table pressure like that, you realize that table pressure is as a result of the what? The cell wall. So it's more or less something like external pressure you are applying to the what? To the solution. Okay. So we have what? We have pressure potential. But pressure potential is more or less some sort of an external pressure that you are applying to the what? To the solution. Okay. So U is the one that is external one. It is not inherent. The solute potential is the word is that sort of water potential as a result of the what? The dissolved solute particles. Okay. So overall, when we come to the word, the water potential, the total water potential, there are two things we look at. It is the solute potential. The solute potential here plus the what? Plus the pressure potential. And remember, solute potential is always negative because solute potential will actually restrict the movement of what? Of even water molecule. Why? Because some of the water molecule, the free water molecule, will bind to the solute, thereby limiting their movement. Then we have what? We have a pressure potential. The pressure potential is more or less the external one that you are what? You are exerting. Okay. The pressure potential is what you are adding, the external pressure that you are exerting to the what? To the solution. And as I have indicated here, in the case of plant cell, you will see that the wall is exerting some sort of what? Some pressure on the what? On the solution. Okay. All right. So that is what we refer to as the what? The Tego pressure. Okay. The Tego pressure. So anytime we talk of the what? The water potential in general, the water potential is the what? Is is equal to the solute potential plus the pressure potential. If there is no external pressure, if there is no wall, then it means that the water potential is equal to the what? The solute potential. All right. So when we talk of water potential, we are talking about the what? The solute potential plus the pressure potential. And remember, the pressure potential is pressure due to the wall, the pressure exerted by the wall. In the case of plant cell, it is the work of the cell wall which is doing the job of the what? The pressure potential. All right. And pressure potential is always positive. All right. Now, please let's take one question here. Let's take a question here. Let's take a question.
Say negative 170 kilopascal.
Okay. Then let me give you this one.
Mr. Patrick,
Yes, sir.
please, you are disturbing us. Please, kindly mute your mic and then your video.
I have done that, but still, you still experience that.
Yes, you open
That's
your
right.
door, closing, banging. We are hearing a written. Please mute yourself. Thank you.
Please, Mr. Juman,
Yes, Anthony.
I think that the banging of the door is still continuing. Please.
So what do I do? He said he has muted himself. He said he has muted himself. The banging, everything we are hearing. Yet he said he claims he has muted himself. So maybe he just have to. I don't know. I don't know what we can tell him again. So let's manage it. Maybe he'll come to his own thing and then.
All right. So please try these two questions and then type your answer. Try these two questions. Write the questions down and try your hands on them. When you finish, please type your answer. All right. Yes, I can see my Beatrice answer. That's beautifully delivered. No wonder it's from a lady. I'm so proud of my ladies here. Okay. Any other answer here? Is that what all of you had? Yes. Any more answers here? Okay. Oh, everybody had Beatrice answer. Okay. All right. So here, when you come to the word, so here, the word, remember the water potential. Water potential. Okay, so let me make WP so that I'll hurry it. The water potential is equal to what? It's equal to, that is a solute potential plus the what? Plus the
pressure potential.
potential. And this
So
will give us
negative 200, negative 200
negative 200
plus
plus
30,
plus 30. And this will give us what?
negative 170
Negative 170
kilopascal.
kilopascal. All right. Then this one, I asked you to calculate the diffusion pressure deficit if the osmotic pressure is 200 APA and the what? And the table pressure is 80. So remember diffusion
DPD is OP minus TP.
because
Osmotic pressure minus
osmotic pressure minus
table pressure.
TP. Okay, and this will give us 200 minus
minus 80.
80, and
That
that
gives
gives
you 120
120
kilopascal.
AP. All right, excellent. All right, so well done, Beatrice, well done, proud of you, well done. All right, so I think please anybody with any issue with the calculation, so that we go over it one more time. Is there any issue? Okay. So when we come to, so let's talk about osmosis in what? In plants, okay? Osmosis in plant, but this one I think is better. All right, let me use diagram first then, but I think I will use this thing to explain rather than that. Hello. Please go ahead.
Not on the calculation, but the unit. The unit for the water pressure.
Yes, I gave them in pressure. I gave them in Pascal.
They were three. The Pascal, the kilopascal, or the bars. Or
Yes,
you
yes.
got another one, ATM. What is the meaning of that ATM?
Atmosphere.
Okay, thank you, sir.
Yeah, thank you.
Okay.
All right. So let's say we have what? So osmosis in plant. So osmosis in plant is basically water moving into plant. Okay. So if you look at my diagram here, okay, we are saying that how would water move into plant? Water will move into plant when the water potential outside the plant cell is higher than the what? The one inside. So let me use blank page, and then let me go for my paint. Okay, let's see whether I could get my drawing. Okay, good. Let me go for, okay, all right, good. So let's see. I have something like this here. This is my, okay, this is my plant cell like that. Okay, my vacuum in there. Good. And then let me indicate the solution. So this one is there is what? Solution here. And remember, anytime you dissolve what? You dissolve solutes in solvent, what will happen? The water potential will come down. All right. So there's some amounts here as well. Okay. All right. So like that. Now, what is going to happen? What is going to happen is that there is more water here. So more water here outside the world. Okay, so let me use blue. Let me use blue. Okay, like that. So let me use this one to indicate water. So let's say these are the water molecules. There's water here as well. These are the water molecules. Water molecules here. All right. So we have our water molecules. Water molecules here. As I said, we have water molecules here as well. All right. So there's more water here. And so where there is more water means higher water potential. Okay. And so let's see the things that will come into play. So you can see that there is solution here. So here we have osmotic pressure at work due to the presence of the what? Of the solute in here. There is what? Osmotic pressure. Okay. And this osmotic pressure will create something we call the what? The suction pressure. All right. That is the diffusion pressure deficit. And we'll draw water from here to here. But the water is going to move. Why? From here to here, because water is where there's high water, there's more water here. And where there's more water, okay, where there is more water, it means that what? More water means high water potential. And so this particular solution here, which is of higher concentration, will what? Will exert the suction pressure. There's osmotic pressure here, which has been created by the solution. And this osmotic pressure, okay, here, all right, we'll use the word, the diffusion pressure deficit to what? To pull water into its content. Okay, and this water will move from where there is more water, which means that a place of what? High water potential to a place of what? Low water potential. So this water will continue moving. This water will continue moving, okay, until the what? Until a uniform mixture is obtained. So here is what? So we can say that here is dilute solution or hypotonic. Hypotonic solution. Okay, this is hypotonic, and this side inside the cell here is what? It's concentrated solution or hypertonic solution. So here, and it is the hypertonic solution that is going to exert the suction pressure on the what? On the hypotonic solution. Well, because hypotonic solution, okay, hypotonic solution has more water, and so there is higher water potential here. So I assume that the water potential here is let's say minus 50 here, and let's say the water potential here is minus what? Minus, let's say 400, like that, minus 400 here. Okay, so water will move from where it is having higher potential than where it is having lower potential. So the water will continue like in this direction. Now it will continue until the time when the two regions, okay, they become what? Isotonic. Okay, so this will continue. The water will continue until the two regions, the solution here and the solution here, like that. The two regions A here and the B here, they become what? The same. When they become the same, we say they are what? They are isotonic. Okay, so when the two regions become uniform in terms of the solution, that one, the amount of water that goes here is the same amount of water that comes out. Okay, so when the environment here, when the cell content in the environment is isotonic, what will happen is that we say there is no net movement, no net movement. There is no net movement of water molecule. There is no net movement of water molecule. So when we have what? So when the environment becomes isotonic, there is no net movement of what? Of water molecules. Okay, and no net movement of water molecules means that the cell structure remains the same. Okay, so let's see what happens. Okay, so now let me walk over this thing one more time. So when you place the cell in what? Let's say this is the cell here, and the environment is hypotonic. What will happen? Water will move from the environment into the what? Into the cell by the process of what? Osmosis. The water will go there by the process of what? Osmosis. Okay, and so the water will continue to go into the cell. The cell will become turgid, but it will never burst. The reason it will not burst is due to the presence of the what? The cell wall. So to become turgid. Now, the water will continue to move. Okay, water will continue to move. Okay, water will continue to move. Okay, water will continue to move. Will continue to move. Okay, until what? Until a uniform mixture. Mixture is what? Obtained in both sides of the solution. All right. So in both sides of the solution, then all right. And when that happens, the water, when the uniform mixture is obtained, it means that the concentration here in the inside the cell and the concentration outside the cell, they are the same. In that case, we will say that the solution is what? This solution is isotonic. The environment, the solution here is now isotonic to what is inside the cell. And when the solution is isotonic, it means that we don't say there's no water movement. No, there is no net
movement of water molecules.
Because the amount of water, okay, no net movement of water, because the amount of water that enters the cell is the same as the amount of water coming out of the cell. All right, so in this case, like that, we say there is no net movement of water molecule. There is no net movement of water molecule here. Why? Because we are saying that the amount of water, okay, the amount of water entering the cell is the same as amount of water coming out of the cell. And it's also the same when you place what? When you place a cell in what? In isotonic solution. When a cell is placed in isotonic solution, okay, when you place a cell in isotonic solution, there is no net movement of water molecule, meaning that when the environment, the solution here and the solution inside the cell, they are what? They have the same concentration. In that case, the amount of water that comes out and the amount of water that goes in, they are what? They are the same. Please, any headache so far? All right. Now, what about if you have a case where the water here, let's say I have a situation, let's say there is water here like a cell is here like that. A cell is here like that. And the concentration here, let's say the water potential here is, let's say, minus, let's say, 300 kPa. And then the outside here is minus 200 kPa. All right, so let's say like this. Now, so let's say that this side is A, okay, cell content is A, and outside the cell is B. Okay, so my first question goes, My first question goes, which A and B, which is of higher concentration? That's question 1. Then question 2. Question 2. Water will move from where to where? All right. Okay, so everybody type your answer for me. Yes.
B is of more concentration than A.
Good. Excellent. And water
So
will move
water
from
will
where to?
move from B to A.
Water will move from?
B to A.
No. The moment you have what?
A to B.
Come again. You said water will
Yes.
move from where?
A to B.
Which one is of your answer? The first answer. What's the answer? The first answer.
So I said the B is of more concentration than A.
Higher concentration.
Yes.
Which
than
one is
A.
of higher concentration?
There is B.
No. Higher concentration means the more you have more negative, it means that if you have more negative here, it means you have higher concentration.
Okay.
So, okay, the moment you have more negative, okay, I didn't even put negative here. So the moment you have more negative, okay, so here, the fact that you have more negative means that your water potential is what? Is very low. Okay, so having low negative value of the water potential means that you are what? You have higher concentration. Okay, so in this one, the higher concentration is A. Okay, and meaning that there's what? There's more water here. So more water here makes this one what? Dilute solution. And dilute means what? Hypotonic solution here. And so in terms of concentration, A is of higher concentration than B. And so B has what? More water. That's why the water potential is higher here than here. So here is negative 300. Here is negative 200. And this is higher. So where would the water move from? So the water will move from here to here. All right. Please, I hope you understand.
Yes, please.
All right. Thank you.
you.
Okay. Now, we are going to talk about water, soil water. Okay. All right. Let me give you 1 minute to go over the notes you have jotted down. Let me give you 1 minute to go over the notes you have jotted down, especially these diagrams that I do make. Please take them seriously. That's what will help you to understand. These are these sort of diagrams that I make. All right. So let me give you 1 minute to go over what you have you have jotted down before we proceed. Okay. All right. So we can move forward now. You can move forward now. Okay, so what we're going to talk about now is where? Let me give a correction. We are going to talk about soil water. Soil water. And when you come to soil water, there are some terms we talk about. Okay, there are some terms we talk about. Okay, so first of all, we have something we call that is the pullard. Okay, now when we talk of the pullard, what it means is the total amount of water present in the soil. So I have soil there. All the amount of water present is termed as the pullard. Okay, so when you talk of the pullard, the total amount of water. Okay, if I take a particular area, the total amount of water available there, okay, that actually gives me the word, the pullard. The total amount of water available. That's the thing. Now, please here do the correction on the slide. Because that's a crescent. Now, the crescent, okay, this crescent is the amount of water available to the plant. So, like, let's take this way. Let's take this way. Okay, let me finish this one. Amount of water available to the plant. Okay, and then we have the HR. The HR talks about the amount of water that was not absorbed after the rain. Okay, so let's see. Let me give simple analogy here. Let's take it this way, that the amount of water available to plants. Okay, let's say at home. Okay, the total amount of money in Adjumant's house, okay, at every moment is, let's say it's 5,000 at every moment, money at home to spend. Now, this 5,000, we have this is 5,000. Okay, this is 5,000, and then out the 5,000, 2,000 of them belongs to the wife. And we all know that at home, if a man has 3,000 and the wife has 2,000, the total amount of money available, okay, to spend is 3,000. So the 5,000 here, so which of this one represents the 5,000 is the amount of money in the house, and wife money, the out of the 5,000, 3,000 belongs to the wife. So the crescent is which one? Is it the 5,000 or the 2,000? Yes. Okay.
Say, to me, I think is the 3,000.
It's 3,000, the crescent.
Yes, the crescent is 3,000.
Excellent. Why? Because we know that the 2,000, this is a very tricky question that I asked, because we know that this is the total amount of money at home, all right? And this is the money. Out of that money, the wife's money is what? The wife's money is 2,000. And you know that this 2,000, even when God comes, it will not be available for the family to spend, because ladies' money is untouchable.
It doesn't go out.
It doesn't go out.
Just like Anna's money. Honest
not
money
because
will never go up.
sometimes you even send credit, call credit, and you, the one who sends the call credit,
Will
they
now
will
call
flash you
for you
for
to
you
call
to
back.
call, and then you wonder that
What
credit
is the use of the
used to
credit?
call, who and who would the credit be used to call? You don't get it.
Ajuman is not
So
always.
here
It's not always.
you can
It's not
see.
always.
All right. Oh, the lady. Oh, ladies are wonderful people. They've explained. Ah, that's good. So here, the total amount of money, the total amount of water there is just 5,000 here, which stands for the here. All right, but this 2,000 wouldn't be available to the plant. Okay, so which means that what will be available to the plant is what? 3,000. That is Ajiman's money. 3,000 here. So these 3,000 is what is available to be spent at home. All right. So that is why it's green. Okay. This one is available to be spent. All right. Good. And then we have the HR, the amount of water that was not absorbed after plant. Okay. Meaning after the rain. So meaning that out of this 5,000, this HR, okay, becomes the what? The wife's money.
The wife's money, untouchable.
Okay, it will never be available to the wife. It will never be available for it to be used to the plant. All right. So the total amount of water available, okay, at home is this plus that. But the one that became available to the plant is this one. And the one that wasn't available to the plant after the run of one that wasn't available, that's the HR. So the total amount of money, the cresat, okay, the cresat is the what? The one available to plant, and then the what? The HR is the what? Is the one that it's actually after the rain, the one that actually went, they are not available to plant at all. So they are not what? That after the rain, the one that actually ran off, okay, it's actually disappeared. All right. So those ones, the HR, they are not available to plant. And so total amount 5,000 available to plant, that's the man's money. And this is the way, the HR, the lady's money. So the cresat and then the HR, when you add the two, we give you the what? The color. Okay, that's the total amount of money, the water in the soil. Okay, all right. And this one, amount of water that is not available to plant. Okay, good. Now, we have another term we call gravitation water. Gravitation water. Okay, now when you talk of gravitation water, this gravitation water, it's why? It's actually referred to the water that actually what? That percolate goes into the water, those pores. Okay, that actually, so this one, those are small, it percolates down. Under the influence of what? Gravity. Okay, so this water is a part of the water that's what? That goes down, okay, through those large pores between the water molecules. And this one, it is sinking under the influence of what? Gravity. So here, the water here Okay, the water here, it's what it goes down. So remember, it is using those large pores. It's going through the large pores. Okay, so because of gravity causes every substance to what to go down. Okay, so this water, the water percolates downward through large pores. Okay, between the soil particles under the influence of what gravity. That's what we call it what gravitation water. Okay, and it's what reaches the low water table. Okay, and then it goes off beyond the reach of plant. So it keeps sinking. All right, so it keeps sinking. Okay, so it will reach the low water table, and then it goes off beyond the reach of plant. Okay, all right. In case the gravity water is available to plant, it must be absorbed. Okay, all right. So in case the is available to the plant will absorb it. Okay, so when it is not so far, so when the gravity water is not too deep, it's not too deep, okay, deep down, then it becomes what available to plants. Then it becomes what available to what to plants. Okay, but gravitational water is what the water that is going through those large pores between the soil particles and then sinking down under the gravity. And then so it goes down, and then to reach the low water table, then it goes off beyond the reach of plants. But sometimes if it is not so far, it's not all down deep down, then at that, and if it's not too deep, then it is plant roots can work and reach it and absorb it. Right? Good. Then we have something we call field capacity moisture. Okay, field capacity moisture. What does it mean? Let's say I have an area there. Now the amount of water retained by the soil particles, okay, due to the water holding capacity of the soil. Okay, so let's take it this way. Let me go and draw. Let's take it this way that I have something like this. I have something like this. Okay, let's see. I have these are my soil particles here. Soil particles here. Soil particles here like that. Here like that. Okay, the soil particles here. Okay, soil particles, soil particles, soil particles, soil particles. Like that. Now, and then let me bring my water. If I bring my water here like this, let's say this is the water here. The water here. Now the amount you see the soil particles can hold up certain amount of water. Okay, between them. Between them like that. So in between the soil particles, they will be holding, okay, the soil particles will be binding, okay, will be holding some water molecules. Okay, we'll be holding the water molecules like that. We'll be holding the water molecules like that. So when we talk of field capacity moisture, it talks about the amount of water retained by the soil particles, okay, due to its ability to hold water. Okay, its ability to hold water. So for instance, if you take something like clay soil, okay, if you take something like clay, soil, okay, clay soil, you see that clay soil, the particles are tightly packed, and so they have what? They have ability to hold on. They can the water molecules can bind to the what? The soil particles. Okay. So when we talk of the field capacity moisture, okay, this one talks about the what? The amount of water, amount of moisture that the soil particles can what? Can hold. Okay, due to what? Due to its ability to what? To hold the or to bind the water particles. The water molecules. Okay, so let's say that's what I'm demonstrating. So these are the black ones are the what? The soil particles. Okay, and their ability to hold these water molecules. Okay, the ability for the soil particles to hold the water molecules like that. That is what we refer to as the what? The field capacity moisture. Field capacity moisture. That is the ability to do what? The ability to hold, okay, the ability to hold the what? The water molecules. Ability to hold water molecules describe what we call as the what? The field what? The field capacity moisture. Okay, so you can see that clay soil that has what? That has a field that has what? That has clear soil will have what? Will have high field capacity moisture, because clay soil has the what? High water retention ability. Okay, all right, good. So when you have this field capacity moisture, what are the other terms that we talk about? Okay, so we have something we call, they actually exist in what? Some sort of this field, this moisture available to what? To available in the what? In a particular field, okay, which is being retained there. They actually tend to manifest in three forms. Okay, what are they? We are talking about what? One, we are talking about what? Capillary water. Then we are talking about what? So this field what? Capacity, the field capacity moisture is being manifested in three ways. What are they? We have capillary water, okay, and then I quite remember when we did the soil science last semester, I made mention of what? The capillary pulse, okay, and then we have the hydroscopic water, and then we have the chemically binded water. So I'm going to walk you through them. They are very, very simple. So these three terms collectively define the what? The field capacity moisture. Okay, so let's start with the what? The capillary water. Remember the capillary, we made mention of what? So this one, we made mention of when we were talking about the capillary, we made mention of that small pores. That small pores, okay, that small pores, okay, small pores between the what? Between the cell particles. Okay, those small pores between the what? Between the water, between the cell particles. Okay, so that's what we are calling what? The capillary water. So you remember the capillary, when we talk of capillarity, anytime you mention capillarity, the word capillarity, okay, capillarity, we're talking about the word, the ability of what? Of liquid to rise through a narrow tube. All right, that's what we call capillarity. Okay, so here, when we talk of the capillarity, we are talking about what? That water that thing to rise through those narrow tubes. All right, that water, that thing to what? Rise through those narrow tubes. All right, it's what we call what? That's the capillarity. That's the capillary. Okay, capillary. That's a capillary. Okay, that's the capillarity. Okay, the ability of liquid. Okay, so in this talk, when we talk of water capillarity, we're talking about ability of what? Of water to rise up through those what? Through those narrow pores between the what? Between, so in the context of water, is the ability of water to rise through those narrow what? Narrow pores. Okay, narrow pores between the what? The water particles. Are you with me? Between the what? The water particles. Are you there?
Doc, is it
Hello?
between particles or water particles?
Oh, look at me. Between the
Between
soil.
soil particles.
I keep mentioning water, so water is in there. All right. So here you can see the capillarity in the, so here the soil capillary, when we talk of the capillary water here in the context of soil, okay, this capillary water, we're talking about the water. So capillarity itself, okay, is the ability of liquids to rise through a narrow tube. But in the context of what? Of soil water, in the context of soil water, okay, soil water, who will say that it is the what? The ability of what? Water to rise through narrow what? Narrow pores between the what? The water, the soil particles. Okay. And so these water, that thing to rise up is what we are talking about, what? The capillary water. So you see, anytime you dig a well, you can see that, you see how the water moves up in the wall. So that is that action is capillary water. Okay, that's water you see to move through those tiny pores, the tiny pores, and they are rising up. You see, they are not sinking. When you are sinking, you sink through the bigger pores, okay, into the what? Into the cell under the influence of gravity, and that water is not available to soil. Okay, when it goes deep down the water table. Okay, but what happens is that some of these water, these tiny pores, okay, the water rise up through those tiny pores as a result of what? Capillarity. And what is capillarity? Capillarity is the ability of liquid to rise through a narrow tube. And so in the context of what? Of soil water, we can say it is the ability of what? Of soil water to rise through the what? The narrow pores between the soil particles. And so this particular what? This particular water is available to what? The plant. This is what rises through the what? The soil. And it's available to what? Okay, the capillary water, all right, water is available to plants, all right. So they fill those tiny, okay, available to what? Available to plants. Okay, so they fill the what? Those tiny pore spaces which they rise up. Okay, they rise up through the tiny spaces, making themselves available to plant roots. Okay, all right. Then we have the hydroscopic water. The hydroscopic water is what? It's held by the soil particles. Okay, so here we are. Let's see something. So this hydroscopic water, look at the analogy I'm going to give, and you will tell me whether it is available to plant or not. Okay, let's say, oh, okay, the answer is here, but I will say that the hydroscopic water is like water, it's like money. The analogy is when ladies money. Okay, all right. This is the perfect. Let me use red. Let me use red here. Ladies' money. You know the ladies' money is never what available. No
That is
matter
right.
what. Yeah, that is the
Exact.
example, the analogy. Okay, the ladies' money is highly hygroscopic. Okay, it's a hygroscopic water. They tend to hold it tightly by adhesive forms. Okay, so in this particular
And Doc,
case,
since you've already
when
used the ladies' man, you've answered the question already.
yes, yeah, oh, thank
I
you.
mean, hydroscopic water is
My
not
ladies,
available for
they are
blind.
very yes, at all, at all, at all, at all, at all. So capillary water is like man's
Money
money.
is our money, and then hydroscopic is the
Yeah, is the
honest
ladies.
money.
Yeah, yeah. So here, this particular water, what is happening here is that the water is here like this. Okay, so this water, okay, there is adhesive force. Okay, okay, this water they are holding on so tightly. Okay, so they are tight like that. So this one, they are more or less binding to the way to the soil particles. Okay, they are very tight. So even though they are in the soil, they are not available. Okay, to the plant root to absorb. Plant root can't draw them.
Say,
Why? Hello.
I want you to, if you can put asterisk to the hydroscopic water, the ladies' money, so that you know it is very, very adhesive force that is binding them.
Yes, Ajubai, you will go to heaven with this behavior. Why? Why are you doing that to my ladies? Ah, don't you know? Eh, eh, so here, this one, it is not available. Why? Because we have force. The reason it is not available is because of this force. The force here. The force here, okay, the adhesive force. So it's a that's the so this one, the soil particles, okay, they are binding to it so tight, okay. Those ladies' money, you know, they use the money to the money will actually bind to the surfaces of the ladies, either through manicure, pedicure, eyelashes, eyeshadow, lipstick, lip gloss, lip balm. So ladies, their money tend to hold on tightly to them. And because of that, the ladies' money is what? Is hygroscopic water. Okay. They form complexes, okay, on their faces, on their bodies. And so that money is not available to be spent at home. Okay, good. So the
Hello, sir.
hello,
Sir, please, can we say that soil that normally have this hydroscopic water is clay soil?
yeah, so which means that hygroscopic even the sandy soil we could have it there, but you see the sandy soil can't have much. Have you seen it? It wouldn't have much. Please, you get a point, right? Hello.
Hello, sir.
Yeah, so it will have, but not much because it can't hold them that much. But the clay soil, okay, the clay soil, they can hold on. They can hold on to the water very, very well. And because they can really hold on to the water very well, they have what? Higher amounts of what? Of the hygroscopic water. They can hold on. They can hold the water tightly. Okay. They have strong adhesive forces. Okay. All right.
Yes.
Okay. All right. You know, so strong adhesive for the forces that, so this force here, okay, so the force will be somewhere here. Let me pick different color here like that. Okay, so let's say the forces will be somewhere here like, so this is the water, the blue one is the water. So let's say the green is the forces. So the force between the what? So this is the force between the soil particle. Okay, so this force here, this is the force between the what? The soil particle and the water. So between the soil particle and the water. So this is the water molecule. All right. And so this force is the what? The adhesive force. All right. So the adhesive force is just holding the water tightly, making it not available, okay, to the what? To the plant root. So plant root can't draw it. Okay, it's just they are binding. Okay, yeah. So clay soil has that high amount. Okay, has that high amount. So just bind it to it tightly. Okay, and that is how come that you tend to find clay soil in what? In waterlogged areas. Okay, which means that they have that high ability, that there's high this adhesive force that they can work. They can hold on to water. Okay, all right. So that's what hygroscopic water. So that hygroscopic water is not available to plants. And then the classic example, so you can see that capillary water will be like man's money, okay, money in a man's pocket or wallet. Okay, that let's say the wallet or the pocket is the small pores, those capillary pores, okay, holes within the what? The cell. And then the hygroscopic water is the water that is binding to the body, the soil particles. So that's the money for the pedicure, manicure, lipstick, lip balm, lip glow. Okay, and that one is what? Hygroscopic water. So in this case, this water is actually binding tightly, okay, with a force. Okay, the force is, so this is the what I'm indicating on my screen. The green is the what? The adhesive force. Okay, all right, the adhesive force between the what? Between the water molecules and the what? The shell. Okay, that is the adhesive force, the water molecules and the what? The shell. Okay, that's adhesive force. Okay, great. Any headache so far? Any headache so far? All right.
Okay.
Now let's go. Yes, please. Any headache so far? Oh, we are
No,
fine.
sir.
Okay, thank you. All right. All right. Okay. Then let's talk about water absorption. Okay, absorption of water. Okay, so parts of plant that tend to, so when you come to water absorption,
Hello, Doc.
roots of plants. Hello.
Doc, please, the
Hello,
last
please.
one, it's the chemical combined water.
Yes. Okay, that's also a good one. Okay. Oh, okay, good. So now my question to you: will chemically combined water, will it be available, okay, to the soil? Yes. That, please, the question. I'm asking you a question back. The chemically combined water. When you talk of chemically combined water, it's like this. Okay. This one here is to be. Let's say it's like this. Okay. Let's see. Let me use this surface too. All right. Chemically combined water. This is not necessarily the. Let's take it something like that. I have calcium. Something like that. Let's say I have. If you remember, when we talk of, let's say, then dots. Let's say H2 water. Let's say H. Oh, like that. Okay, so let's say what I've written here. Let me go down. This is what I've written here. Chemically combined water. So you see, this one is, let's say, a chemical. All right. And this is a water molecule, but it is what? It is they are bound to what? Okay, they are actually binding to this particular substance in the soil. Please, do you understand what I'm saying here? Is water all right? It is water all right, but look at where the water is. So this water is actually is what? It's combined with this particular chemical. All right. And so this is not available to the soil as well. Please, do you understand what I'm saying here? Hello? Hello? Are you there?
Yes, yes,
Hello,
yes.
sir.
Yeah. So this is water molecule, all right. But this water molecule is chemically chemically attached to this. Okay, it's chemical, not physical. For hygroscopic water is just adhesive force. Adhesive force here. All right, like that. Okay, that they are just force of we have two main forces of what two main forces of attraction when it comes to molecules in contact. We have cohesive. Cohesive is, well, let's say if I have water here, water, like this force here is cohesive. This one is cohesive force. The one here is cohesive force. But water, soil, this one here is what? Adhesive. Because they are not, when the molecules are the same, it's cohesive. But when the molecules are different, they are what? Cohesive. These are physical forces. Okay, physical forces. Now this one is chemically. So this one is more or less is actually combining to this true chemical reaction. So it's not available. So this is, let's say, calcium sulfate with water molecule attached to it. So chemically combined water. Okay, all right. So this one here, we have, this is water molecule. Okay, we call this one hydrated water. This water molecule here, like that, is what? This water molecule here, okay, is chemically binding to the calcium sulfate, and that water wouldn't be available to plants. Okay, please, is it clear there? So hygroscopic is physical, that's true. Adhesive force, like water and soil, that's adhesion. Water cohesion. Okay, so this one is like we are attached to each other by what? By adhesive force, and that particular water is not available for plants to use. Okay, it's not available for plants to use. Okay, so the one that is directly available for plants is the what? Is the capillary water. Thank you. All right, then let's talk about what? Absorption of what? Absorption of water. Okay, absorption of water. Now, so we have, when it comes to absorption of water, we have what? We have various terminologies that we talk about. Okay, so depending on what, because we have the plants, plant can absorb water. Sometimes stem could absorb, sometimes leaves could absorb water. Okay, so we have something we call hydrophyte. Those plants that we described on hydrophyte, they use their entire body surface for absorption of water. Please, can you give me one example of plants we can describe as hydrophyte? We did plant morphology last semester. Can you mention any plant, any Any plant that will use the entire body surface to absorb water? Anybody? Yes.
Fence.
Yes. One is where?
Sir, fence.
That is not really
Moose.
example. Yes, example. Yes.
Moose.
The moss is the what? Yeah. Yes, you are right. That's excellent. One. Okay. All right. That's excellent. One. So here, the classic example are the what? Are the mosses. Okay. Mosses and liverworts. Okay, those are the technically called what? Bryophytes. Okay, so they will use their entire body. Okay, they will use the entire body for what? For absorption. So those hydrophytes, they tend to use their what? Entire body for absorption of water. Okay, all right, good. And then some of them also tend to live in water, like for instance, some of them too, they actually live in water. Like usually most of the hydrophyte, they live in water body. So they are going to use their entire surface to pick up water. All right. Now, what are the factors that tend to influence it? Okay. Okay. So if you look at if you come here to let's say water absorption, okay, and then leaves affect water intake. Okay, how? My question is that, okay, when we have leaves, okay, how does leaves, okay, all right, let's see. Oh no, this one is in the wrong place. Okay, let's see. Okay, all right. I think we are fine. Okay, great. Okay, so let's take leaves. So leaves can absorb water. Some plants, not all plant leaves do. And even if it's absorbed, remember leaves, when we did the detailed structure of leaves, let me draw this one here. Remember, I drew this thing for you, and we have the gut cell here like this, the gut cell here like that, and so water vapor can actually enter the leaves through here, through this space here, through the space in the stomata. So this is the stomata here. All right, so this is the gut cell. Okay, the gut cell here. This is the gut cell, and this is the stomata. All right, good. So let's see. All right, so factors that can affect water intake. Let's say in terms of leaves, what will affect water intake in terms of leaves? Let's say, let's go. Okay, so let's say for leaves. Okay, what are the factors that would determine the word that will affect intake of water by leaves? Yes, so one is the word, the structure and permeability of the cuticle. Okay, one, we are looking at the factor that will affect water intake by leaves. Now, remember on the surface, if I come here, if I take this thing, if I come here and I take something like that, if I take, this is my leaf. If this is my leaf like this, like that, okay, like that. Now on the surface of the leaf, it has what? Cuticle. Okay, and this cuticle is waxy. And okay, I can write at the top here. The cuticle is what? Cuticle is what? Waxy. All right, and you know here it's shiny as well. So we have the waxy cuticle here. Okay, so this waxy cuticle can affect the what? That's what is covering the epidermis. So the thickness, okay, this waxy cuticle is usually the cuticle is impermeable to water. Cuticle is impermeable. Okay, impermeable to water. Cuticle is what? It's impermeable to water. Cuticle is impermeable. It's impermeable to what? To water. Okay. Cuticle is impermeable to water. All right. So in terms of what factors that affect water intake by the leaves, the cuticle, okay, the thickness of the what? The permeability, that the structure and permeability of the cuticle and the epidermis. When it comes to the epidermis, they are the cells here. So let's see if I take this the leaf like this. If I take this the leaf, the cells on the surface of these leaves, okay, the outer part. Let me go to the detailed structure. Okay, let me come here. The detailed structure of a leaf, okay. Let's say if you look at the detailed structure of a leaf, if you can remember, all right, if you draw the structure of a leaf like this, okay, all right, like that. So what is going to happen? So here on the surface, on this surface here, the cells here, this layer is the what? The epidermis. The layer down here is also epidermis. So even the gut cell, this gut cell I've indicated here, this gut cell, the gut cell here is also epidermal cell, but it's a specialized epidermal cell because of the shape and allowing. Okay, so the gut cells, so this cell forming the outer part of the leaf are all what? Epidermal cells. So the cell here, all these cells here are epidermal cells. Okay, all those cells are what? Epidermal cells. And what is lying on top here? On top here, okay, let me paint it. So this structure here, okay, on top here is the what? Is the cuticle. Okay, so you can see that the cuticle is found on the what? On the upper surface of the leaf. All right, so that it will reflect the heat radiations. Okay, all right. So the cuticle is here. So this yellow thing that I've indicated here, this one is the what? The yellow structure here. This yellow structure is the what? Is the cuticle. Okay, and inside there we have the other cells. We have the palisade mesophyll, tightly packed like that. And then we have the spongy mesophyll that are loosely packed. They are loosely packed with a lot of air spaces. They are loosely packed. Okay, like that. Okay, like that. So the palisade are tightly packed. And then on top here, we have the what? We have the cuticle and we have the epidermis. Okay, we have epidermis down here. So when it comes to factors affecting how water uptake by leaves, the structure and permeability of the cuticle and the what? And the epidermis tend to affect it. So one, the structure and permeability of the cuticle in the epidermis. Well, this is the cuticle, The yellow, what I've highlighted here on top, and the epidermis is what is here. Okay, and then another thing is a word. That's the hairiness of the leaf surface. Remember, when you have a lot of hairs on the surface of the leaves, the hairs could trap what? Could trap moist. Hello.
Hello, Doc. Please.
Hello, please.
I think you made a point that the cuticle is impermeable, but we have some of them that could allow.
It's actually impermeable in most cases, but you can get some leaves that the cuticle is not all that thick. I've seen occasionally, and then by the back here, even the back here like that. You see, if you have very thick cuticle, it's impermeable. Yes, that's right, to water. But if you have thick cuticle, it means that even amount of water that will evaporate from the leaf will be reduced. Are you with me? If for instance, desert plant, let me put it, let's say desert plant, okay, have what? Have a very thick cuticle on their leaves to reduce water loss. You get a point, right? So the thickness of the cuticle, okay, the cuticle is very, very, very thick. Okay, so if the cuticle is very thick, it means that it will not allow water to just leave just like that. But even still, no matter what, certain amount of water will evaporate once you apply heat onto the surface. Did you get a point, right? Okay, it's waxy, just like maybe our skin. Okay, you don't see water just dripping, but you see that you expect that when water is coming, water doesn't really, let me use my palm, our palm. Water doesn't really come, you don't see water coming out of our palm like that. Okay, because of the nature of our character. But still, some amount of water is lost there. So some amount of evaporation can occur through the cuticle, even though it is impermeable to water. That is how we describe it, because of the waxy nature of it. Okay, it's not something that water will come and on top here and then it will just pass through the cuticle like that, pass through the cuticle on the surface here into the they say the palisade mesophyll here. No. Okay, but when heat is applied here, some amount of water can be lost through the cuticle, no matter how thick it is. But just that if you are very thick, the amount of water loss is it's reduced significantly. Please, you get argument? Hello, please, you get argument?
Yes, please.
Okay, good. Yeah, so it is thick. It is impervious. But when you apply heat, the sun heat can cause some amount of water vapor to come out through that. Okay, so when we come to even 3 types of water loss in plants, we mentioned cuticular transpiration, which means that some amount of water vapor as a result of the heat from the sun can cause water vapor to exit through the cuticle. Okay, all right, great. Well, that's a brilliant question. Well done. Okay, so we have the hairness of the surface of the leaf. Okay, so this hair, the hair on the surface, the hair can trap moist. Okay, all right. So water uptake could also be influenced by the amount of hairy structures on the surface of the leaf. Okay, all right. And then sometimes, as we just said, wetting surface. Sometimes some leaves, their surface could be very, very wet. Like which means that the cuticle may not be all that waxy. You know, some leaves like that, there are some leaves, when you pour water on the surface, you can see the surface is very waxy. The cuticle is so thick, okay? and then so there's the impregnation of the cuticle is very high. So that one, when you even put your hand on it, you could even feel the cuticle. Other leaves too, the cuticle is not all that much. They are very small, and then so the surface of the water itself looks quite wet. Okay, so some plant leaves the surface of the leaves are wetting. Okay, they have more of wetting surface. I mean, just like the way human beings are. Some people, if you just touch their palm is very soft. Okay, especially the ladies. If you touch their palm, the surface of the palm is quite wet as compared to ours. Okay, all right. So likewise in plants as well. Okay, some of the leaves, the cuticle is not all that thick. Okay, or maybe the amount of the cuticle in there is not all that much. So the surface is wet. It's quite wetting. Okay. Then another thing is also the internal environment. Okay. If the internal environment, okay, so internal environment has what? Water deficient. Okay. If you don't have water, let's take it this way, that like what I have done here. If inside the plant here, if inside the plant here, okay, if inside the plant here, then there is what? If inside the plant here, there's much water here inside this side. If there's much water in those spaces here, then the plant wouldn't absorb a lot of water. Okay, so if the internal environment of the plant is also what? It's also deficient in what? In water, then it means that there will be what? There will be water deficit. And this water deficit will create something like called the suction pressure, as we talked about previously. Okay, so the internal environment, okay, all right, those cells, those parenchymal cells in the what? Here, the palisade mesophyll and then the spongy mesophyll. Okay, so the internal environment, okay, all right, if there is what? There is deficit. Okay, if there is deficit in the internal environment, then that can also what? Influence the what? It can also influence the water uptake by the leaves. Okay, so quick recap of that. So when it comes to water uptake by plant leaves, okay, it could be influenced by the structure and permeability of the cuticle, as well as the what? The epidermis. And then we talk about the what? The hairy structure, the hairy nature of the leaf surface, the wetting nature of the leaf surface, and then the what? The water deficient of the what? Of the internal environment. Whether we have enough water here, okay, if there is enough water here, of course, there will not be any deficit for the leaf to draw more water. Okay, all right. I think we've gone for 2 hours for some of you. Okay, so let's break at 9:10. Okay, so let's talk about the roots. Okay, the roots. Okay, let's talk about the roots. Okay, absorption by the root. Okay, great. So when it comes to the root, let's see some of the factors. Okay, all right. So remember, last semester we did what? We did the root structure. Okay, roots. Okay, so if I should go to the root structure again here, let me pick this. Okay, so let's say if I pick the root structure here like this. Okay, you remember that this side is the root cap. The root cap here. All right. So this is my root cap there. Okay, root cap here. And then we have this side here. Okay, that's the region of what? That's the meristematic region. Meristematic region. That's our region of division. Region of what? Of division. That's where the cells here tend to divide. Then the next one is the what? What's the next region? Ajima, what's the next region? Region of what? Yes,
Region of elongation.
Elongation.
Elongation, good. And after region of elongation, what's the next one? Region of what?
Cell difference.
Region of, what's the next
Cell
one?
differentiation. Cell
Region of
differentiation.
differentiation. What's another term for region of
Cell
differentiation?
differentiation.
What's another term for
Cell
region of,
maturation.
okay,
Cell
maturation.
maturation.
Okay, good. Maturation. So that's a maturation region here. Maturation or what? Or differentiation. All right. And that place, what you will see there, is the what? The presence of what?
The root hair.
The presence of root hairs. Okay, the root hairs, they indicate, don't forget that. So here, the region of what? The region of what? Okay, let me get the maturation region. Maturation region. That is the, we have the word, the root hairs. Okay, that is the, so the presence of the root hair indicates the word, the maturation region, or the region of what? Differentiation. Okay, beautiful. All right, great. So you do this one already. Okay, so here we have what? So you can see that the root hairs are cells. Okay, by the way, can you give me characteristics of root hair? What are the aesthetics of root hair? Now, can somebody tell me some of the characteristics of root hair? Let's see. Aesthetics of what? Aesthetics of what? Root hair. Root hair cell. Yes. What are some of the aesthetics? Yes. Talk about the cytoplasm. Does it have dense cytoplasm? Hello? Oh, you guys are tired? Okay, well, let's give ourselves a break. Okay, Ajiman. Hello, Ajiman. Are you there? Yeah. Okay. So so how many minutes break do you want? How many minute break? Because people just woke up and they join the class.
30 minutes. 30 minutes.
30. Okay. All right. So 30 minutes break. Okay. So that, but please wouldn't wait for you. Okay. All right. So please, I will keep my screen on, and then please, so get something to eat. I can see the response is slow because people are not talking, people are hungry. So please just get 30 minute break. But if you take 30 minute break, I'll add about 10 minutes to the time. Okay. All right. So let me break in here, and then when we come, then we continue from here. All right. Thank you. All right. Hey, Nicola, what's your example? Nicola, she said what? Side check money. So I don't think the money available use at home is 3K. Hey, Nico, this is your example. All right. All right. So please go and get some tea and then some cocoa like that. And then after that, we'll continue. Thank you. I think we'll kickstart because we can't wait for people forever. Okay.
All right, yes, Doc.
Yeah, we need to start because I mean we gave time. If not, we'll be waiting forever. Okay, so
Okay.
please let's kickstart. Okay. So I asked of word. So I could see Ajiman has written some points in the word. In the section here, characteristics of root hairs, thin cytoplasm, thin cell wall, long narrow extension, large surface area, that's correct, large vacuum, and no cuticle. All right. So these are correct points that he has enumerated here. All right, that's great. Okay, so in addition to that, on my slide, you say that they are what they have they are highly. I mean, it's a plant cell. So plant cell would definitely have a cellulose, and then the primary cell will also contain pectin, okay, which is called pectin is the substance, but you have the pectic substance like calcium pectate. And then they are highly hydrophilic in nature, which means that they love water. And then the cell will act as well as a permeable membrane or as a permeable layer. Okay, all right. So let's see. Now when you come to let's see this particular image here. Well, I can't really play it here because I think it's, but what happens is that what I have here is something we call transpirational stream. That is water from the cell making it all the way to the leaves. All right, so that is the transpirational stream. Okay, water from the cell making it all the way to the leaves. Okay, that's a transpiration stream. All right, so transpiration stream here, so the water inside the soil here will be absorbed by the root hair. And then remember, as Adiman pointed out, the root hair, they are numerous. And the reason they are numerous is to provide light surface area for absorption. Okay, they provide light surface area for absorption. And then, so it will just rise up and then eventually get into the leaves. And then in the leaves, some are going to be lost, okay, through the what? Through the cuticle or through the stomata. Okay, so right from all the roots all the way up, okay, to the leaves is what we term as what? Transpiration stream. Okay, all right. So here we are going to talk about the mechanism of water absorption. How is water absorbed from the soil? Okay, so that's basically what we are going to talk about. So the terms here, they are not new to you. Okay, so we have the word, the pressure deficit, the diffusion pressure deficit, which we know the formula. That is what the diffusion pressure deficit, okay, which is the same as the suction pressure, diffusion pressure deficit, which is also known as what the suction pressure, okay, is equal to what? It's equal to osmotic pressure minus what? Ego pressure. All right, so this is not new to you. All right, so water diffuses into the root hair as a result of what? Diffusion pressure deficit. And what it means, diffusion pressure deficit gradient, what it means here is that there is what? The cell contains of what? Cell contains of the plants of the root hair root hairs tend to be of what? Of higher concentration, okay, higher concentration, which means it's more of hypertonic, okay, and because it is hypertonic, meaning that, so if you are hypertonic, it means that your water potential, your water potential is low. Okay, you have low water potential. All right. And then when you take the soil has what? Has more water there. So more water in the soil makes the soil becomes what? Soil becomes hypotonic. The soil becomes hypotonic, and then hypotonic means that you have what? You have high amounts of water. High amount of water. High amount of water. And high amounts of water simply means high water concentration. Okay, and high amounts of water means high water potential as well. All right. So that is that. Okay. So high amounts of water means high water potential. Okay, beautiful. Now, so which means that I think what is down here is what I've explained here. So the cell sap is the content of the word. That's a cell sap. Okay, that's a cell sap here. It's referring to what I was referring to as the cell content of the root hair. All right. So this cell sap has what? High concentration of solute. And high concentration of solute means low water potential. Okay. And so water enters along the word, along the diffusion pressure deficit of the cell sap. Okay. So which means that this will cause water to move from what? From where there is more water to where there is what? Less water. Okay, let me keep these notes there so that those who want to jot down something. Okay, we move from there to where there is what? Less water. Okay, we move from there to where there is what? Less water. All right. All right, so we have the word where there's diffuse here. So we have the word. So it becomes hypotonic. Okay, and then the cell content is what? Hypertonic because of the word. The cell sap. The cell sap here, that's the content of the cell. Okay, contains a lot of solute. And so the water potential there is low. So water will move from the cell along the word, the diffusion pressure deficit. Okay, good. Until it's stretched. So remember, it's going to stretch until the elasticity of the wall is sufficient to balance the osmotic pressure of the solute. So remember, water will keep entering until the Tego pressure is balanced everywhere. Okay, and I think I've explained that one to you already. All right. So let's see, what are some of them? There are a lot of theories governing water absorption. Okay, you know, we always say that water absorption is by what? Osmosis, and it doesn't require the use of energy and stuff like that. So, but there are a lot of theories governing water absorption, theories that people have proposed over the years governing water absorption. Okay, and so those theories is what we're going to look at, and then we'll talk about them. So there are two approaches. Okay, one of them is active absorption, that some school of thought is saying that, oh, the absorption of water is actually active process. Okay, and therefore it requires energy. All right. And then and with that theory, with that active process, there are of two types. We have the osmotic one and non-osmotic one. Okay. All right. So this is basically what we are going to discuss now. Okay. So people came out with various theories governing water absorption. Okay. They came out with various theories governing water absorption. All right. So let's start with also under the word. We have the word. Let's start with the osmotic. Okay, we are starting with the osmotic theories. Okay, and this osmotic theory, they were actually proposed by Atkin in 1916 and Priestley in 1922. What are they saying? Okay, they are saying that water is absorbed due to osmotic difference between the soil water and the soil sap, which is true. I mean, we all believe this one. Okay, so under the osmotic theory, what they are saying here is that yes, that water absorption is due to the differences between the what, between the differences in what, that's the concentration of the two regions. That's osmotic what, the osmotic pressure differences between the two regions. That's between the soil sap and then the soil water. Okay, so that's what that's what establishes the concentration gradient. Okay, and this osmotic pressure of water remains what, below 1 atmosphere pressure. All right, so what he's just saying here is that the osmotic pressure of the what, of the soil water is below that of what, atmosphere pressure, and that of the soil sap is between 2 to 8. So you can see that. So what they are saying, what Atkins and Priestley were saying, that yes, the osmotic pressure is less of the word of the soil water. Okay, it's less than that of the word, the soil sap. Okay, so he says that of the soil water is always less than 1 atmosphere. Okay, meaning 1 atmosphere, like this is a unit of pressure. The unit of pressure, you know, you can measure pressure in terms of Pascal, you can measure pressure in terms of bar, and you can measure pressure in terms of what, atmosphere. So what he's saying here is that the pressure, the water pressure, the osmotic pressure of the soil water. Okay, remember soil water is more or less a solution. Its pressure there is less than what? It's less than 1 atmosphere pressure. But that of soil sap is between 2 to 8 atmosphere. And so if this pressure, so we can see that, let me go and take my this, well, let me explain before I will draw. Then if the cell has what, high osmotic pressure, then the pressure deficit is what is going to what? The pressure deficit is what will pull the water. Okay, so the higher pressure deficit here, okay, the higher pressure deficit, okay, of the cell sap is what will cause the what? The endocytosis. Endocytosis is whereby the influx of what? Of water across the what? The cell membrane into the cell. Okay, and when they finish this theory, okay, what did they do? They say the evidence of that is what? The evidence of that is the root pressure. Okay, root pressure. That root pressure is okay. So let's see. Now let me use this let me take my diagram here and then draw. So let me start here. So what he's saying here is, now I have this plant here like that, and then we have my roots here, my roots here, my roots here, my roots there, and these roots here, there are cells here, there are cells here, cells here. Okay, and these cells, okay, they have solutes here, you know, they have solute concentration. Okay, solute all dissolved, sugar and salt all dissolved here, making here hypertonic. So hypertonic means that, and then I have water outside here. I have water outside here like that. water outside here like that, like that, like that. And so this one will absorb water here. Some will absorb water there. So what he's saying here is that the pressure here is, let's say, between 2 to 8 atmosphere. And the pressure in this soil here, so this is the soil here, the soil here, the soil here, all right? The pressure there, let's say it's less than 1, so let me pick 0.6 here like that. And so you can see that the osmotic pressure here, the osmotic pressure here, and the osmotic pressure here, this one is higher. And because this one is higher, it will create something what we call it what? Diffusion pressure deficit, which is also known as a word, the suction or the sucking pressure. Pressure, like that. So it is that pressure that will pull the water. Okay, and when water is being pulled, the water will move from where there's high water potential, to what? So here being what? Concentrated solution, here we have a low water potential. So there is a gradient that has been established, and the gradient, the establishment of the gradient, the concentration gradient, is what is creating the diffusion pressure deficit. And this one will pull the osmotic pressure here is higher than here, and this one will pull the water here, okay, into the cell sac. And as it pulls, remember here the water, this is hypotonic solution. And so the hypotonic solution will have more water, and more water means a higher water potential. And then less water means low water potential, right? So that is that. Okay, good. So this is what the osmotic theory is saying. Osmotic theory is saying, what osmotic theory is saying is that the water absorption is as a result of what? Differences in what? Differences in osmotic. Please mute your mic. Differences in osmotic pressure. And these differences in osmotic pressure is created by what? It's created by the what? Differences in concentration gradient. Okay, gradient. And this differences is causing something we call diffusion pressure deficit, and which is also known as the word, the sucking or the suction pressure. And this suction pressure will pull, okay, will pull water to the concentrated region. But remember, the water will move from where there is more water, and more water means high water potential, and less water means low water potential. So I think that the osmotic theory suggested by proposed by Priestley and Atkins, it makes sense. That's basically what we all abide by. And then what's the evidence? So what the evidence is saying, that the evidence to substantiate is that they say there is occurrence of root pressure. Okay, the root pressure All right. So there's root pressure here. All right. So the root pressure, the fact that so which means more or less the fact that when you come to the root pressure works this way. When you cut this root here like that, if you cut this wood here like that, let's see, if you cut the wood like this, like that, okay, you cut this wood, what will happen is that the root pressure will cause what? Fluid to ooze out of the root. Okay, so if you cut a tree, okay, if you cut the tree down like that, if you cut the tree down like that, you see that when you cut it, still some liquid will ooze out of the plant. And this liquid that will ooze out of the plant is because of the pressure deficit, which causes water to be pulled out of the soil upward. Okay, so the evidence supporting the osmotic theory of water absorption is the root pressure. That the root has a higher osmotic pressure, okay, that is drawing water along its concentration gradient into the plant. That's why when you cut the roots like that, okay, you see that still water pulls out, which is the root pressure. Okay, so the root pressure here is evidence supporting the osmotic theory. Okay, now this makes a lot of sense, but let's see something here. Now let's see the objection to that. So the osmotic theory has been proposed, but let's see the objection. The objection is that, objection to the osmotic theory is that, okay, difficulty can when movement of water from cortex of cells to the xylem. Okay, all right, so they say that, you see that if you remember when I taught, okay, so let me finish this one, then I'll use the diagram to explain it. Okay, movement of water from the cortex of cells to the xylem cells, okay, takes place because xylem contains comparatively dilute sap, low osmotic value. So roughly about 2 atmosphere, less than 2 atmosphere, as against several of the cortex cells. Okay, so look at the argument. If the argument is saying here is that then there will be a difficulty will come when doing the movement of water from cortex cell to the xylem, to the xylem. Okay, all right, and it takes place because xylem contains comparatively dilute water. Okay, so let's see. Let me use diagram to explain so that to be clearer. All right, so if I come here like that, if I come here like this, now let's take it this way. What we are saying here is that according to the osmotic theory, it means that the water is moving up. Okay, it's moving up here because water, the cell here has about, let's say about 5 atmosphere, and the cell here is, let's say 0.8, okay, in terms of osmotic pressure. So there's more water here. Okay, osmotic pressure, remember, is created as a result of the solute dissolving in the solvent. So what this theory is saying here is that to move up here like that. Why? Because the cell sap has 5, okay, and what is in the cell is less than 1. So let's say 0.8, and this will cause the osmotic pressure to work. The osmotic pressure to draw water along its concentration gradient into the cell. Okay, that's what it's saying. But the objection is saying that then how come? You see, if the water is absorbed by the plant root and it goes into the cell, the parts of the cell, if you draw the structure of the cell like this, The structure of the cell like this, of the stem. This is the structure of the stem. Okay. Now, inside the stem here, the stem. Okay, the vascular tissues are located here. So this is the roots of plants, like that. So the xylem, let's say this is my xylem here. Okay, and let's say this is my phloem there. Let's say the phloem here. Now, so the argument is this. Okay, if you are saying that, now let's say this is the root here, like this. Okay, so the root here, water is here, so I picked the water because here is what, let's say 5 atmosphere, and the water here is what, 0.8. Okay, like that. So this is 5 atmosphere, 0.8, and because we've drawn the water here. Now, how do we explain water moving from this side? Now we've gotten, okay, the roots has succeeded. Now this side is the cortex of the what? Of the stem, of the roots, right? This is the cortex of the roots. So the cells here, okay, these are the cortex, the cells here. How would the cell here move the water to this side? Because studies has also shown that inside here, within the cortex, okay, the cell sap are almost the same. So the cell sap are almost the same. They are about what? They are about less than 2 atmospheres. So they are about less than what? 2 atmosphere. And the cell sap, they have comparative content. So how can the water move from, now that you've absorbed it from here to here? Now it is moving from here. The xylem is here. The xylem is going to transport the water up. So this water should make it to the xylem here. Now, how do we explain how the water moves from this cell in the cortex to this one if 2 of them have comparative what? Concentrations? Okay, and beside, we are saying that the osmotic pressure here, or right here, is about, let's say at the root hair, cells is about 5. So which means that even this pulling water here, now what is here is even less than that of the root hair. So then how will it move from here all the way there? Okay, so that's a point 1. Okay, which means that the objection of the theory that then yes, you have succeeded. Now, so this is the part of the cortex here. Let's say these are the cells of the cortex, and this is mine. So let's say we have the cells of the cortex. You know, the cells of the cortex, they will move, and eventually they will get into something here. We call it Casparian strip. Okay, so we have the pericycle, and inside the we have the Casparian strip like that, and then here we have the what? We have the let's say the xylem here. Now, so we are saying that what is here, this and this, they have comparative concentration. So how can it move? How can water move from here to here? So that's the first objection. All right. And then the second objection is this: water can't enter the trachea. Okay. Remember, the trachea are made up of what? The trachea, if you could remember, trachea are made up of tracheids are made up of sclerenchyma cells. Sclerenchyma. Cells. Tracheids are made up of what? Sclerenchyma cells. Okay, tracheids are made up of sclerenchyma cells. Now, if tracheids are made up of sclerenchyma cells, and this sclerenchyma cells, we all know they are what? They are dead. They are dead at maturity. Sclerenchyma cells are dead at what? At maturity. Okay, okay. We know that sclerenchyma. Okay, we are talking about what? We are talking about tracheids. Okay, tracheids. You know, the tracheids are the what? Tracheids are these structures. These are, let me take a marker here. Tracheids are these structures. These structures like this, okay, forming the what? The xylem, okay, like that, okay. So these are the tracheids, okay. Looking at having a shape like this, a shape like it tapers at both ends, holes on them, with holes on them. All right, okay, like so. These are tracheids of the what? Of the xylem. So now this tracheids, the question is that if we are saying that it's supposed to go through the semi-permeable membrane, but the tracheids are made up of what? Tracheids are made up of sclerenchyma cells. Okay, cells that are what? Sclerenchyma cells that are what? That are dead. That are dead at maturity. And so if it is dead at maturity, then it means that dead cells wouldn't act. It's the cells of the dead cells cannot work, cannot act as what? Act as semi-what? As what? As semi-permeable membrane. So that's the argument that dead cells cannot act as what? As semi-permeable membrane. And so the reason being that if you are saying that the water is going by osmotic theory, as it's being suggested, the first one is that then how would water move from this from cell to cell of the cortex, which would tend to have what? Comparative what? Cell sap content. They have comparatively low value of that. And then second point is that how will the water, based on this theory, water can't enter into the trachea. Please mute your mic. Please mute your mic. So how would the water enter the trachea? Which means the water cannot enter the trachea because the trachea is made up. Remember, trachea is made up of what? Sclerenchyma cells, and sclerenchyma cells are dead cells at maturity. And so based on that, then it is not possible for what? For water to enter the what? The trachea. So this is the counter version of the osmotic theory, that movement of water, okay, across the what? The cortical cells, the cells of the cortex to the xylem will be difficult because one, they have comparatively same what concentration, and also the concentration there, the cell content there, the osmotic pressure is lower. Okay, it's lower. So how would the water move if the osmotic pressure there is relatively lower? Okay, and then the other point is that then it means that if you are still sticking to the osmotic theory, then how would the water enter into trachea, which is made up of sclerenchyma cells that are dead cells? Because with dead cells, it means that the trachea can't act as well as semi-permeable membrane. Okay, and so based on these objections, then people came with what? Kramer and Thiemann. Okay, so Thiemann and what? Thiemann and Kramer, okay, came with what? With a non-osmotic theory. And what is the non-osmotic theory saying? Okay, what is the non-osmotic theory saying? What non-osmotic theory is suggesting is that absorption of water is active process, but occurs due to what? So to them, they are saying that water absorption is what? It's not osmotic process, but it is what? Active process. Okay, and meaning that they are occurring due to what? Non-osmotic reason. Okay, they are occurring due to which means that, remember, osmosis is passive process. Okay, but non-osmotic, okay, means that it's an active process. Okay, and even what? Against what? Diffusion can move, water can even move against what? That the diffusion pressure gradient. That is what they are saying. That even when, according to what this theory is saying, that even when the water here, even when water is low, there's low water here, low amount of water, low water. Let me use that example. So to them, what they are saying here is that if this is my plant root, if this is my plant here, okay, this is my plant here, like that, okay. What these people are saying here is that even when there is water here, okay, water here, and there's more water here, still plants roots will absorb the small water here. That water absorption occur by what? By active process, and then can even go against the what? Concentration gradient. The pressure gradient can go against it. That even this one means that even when there is more water here, the small water here will still be absorbed. That is according to their theory, the non-osmotic theory. Okay, all right, that's non-osmotic. What's the non-osmotic theory? Suggested by what? Kramer, and then there's a Tiemann. Okay, that's what they are saying. And remember, if it is active process requires what? Energy. Remember, it requires energy in the form of what? ATP, right? You have to require energy in the form of ATP. Okay, from cellular respiration. All right, if it is active process, then it will require energy. Because once you are saying something is active process is not free, energy is required for active process to occur. So, which means that it will require energy from what? From cellular respiration in the what? In the plant cells. Okay, to support the what? The process. So that's what they are saying. Kramer, and then what? And then the Tiemann, that's what they suggested. Okay. And what is their evidence? What was their evidence? What was their thought? Okay. Remember, in the osmotic theory, the osmotic theory, you realize that those two folks, okay, actually supported their theory with what? With pressure. Okay. But when you come to the non-osmotic theory, you want to see that what is the evidence, what are the things that they are using to substantiate their claim that water absorption is not osmotic process, but it's an active process and can even go against the concentration gradient or the diffusion pressure gradient. And for that matter, it requires what? ATP energy, okay, from what? From cellular respiration. So let's see what are their proof. So according to them, they are saying that, okay, rooting of fruit occurs in non-aerated soil, such as flooded area. So their point is that roots tend to die. It dries out. Okay, roots of plants tend to do what? Tend to dry out in what? In non-aerated what? In non-aerated soil. Okay, even when the place is flooded. Okay, and their reason being that the water is what? Indicate that water is absorbed by living cells under aerobic condition. Aerobic condition, that's what. So aerobic condition is what? Aerobic condition is respiration that requires what? Requires oxygen. Respiration that requires what? Oxygen. All right. So according to them, according to the evidence they are using to support their claim is that even when the place is flooded with water and there is what? There is no air in the soil. Okay. the roots will still dry out and die, simply because the flooded area means that if there's no oxygen, okay, for the plant's root cells to respire, to generate energy, okay, then to support the absorption of water, then the plant is going to die. So to them, what they are saying is that roots will dry out, okay, all right, even in flooded area where there is no air in the soil, okay, where there is no air in the soil. Why? Because the cells of the roots require oxygen for cellular respiration to generate ATP. All right, that will drive the process. So if the ATP is not there, then what is going to happen is that the absorption of water will not occur. So their argument is based on the fact that even in flooded area, roots of plants can still dry out. Reason being that there is no oxygen in the soil. Okay, there is no oxygen in the soil. Okay, if there's no oxygen there, the roots will still wilt. Okay, so that is one of their arguments. And then another one they are using is that they are saying that if you use respiratory inhibitors such as potassium cyanide, okay, all right. So remember, I don't know whether I taught you this one, but remember that when you do the cell biology, okay, when you come to the cellular respiration, there are three main processes, okay. There are three main processes in cellular respiration. We have what? We have something called glycolysis. Let me go and then oh, look at me. Yes. We have something we call, let me come here. Okay, so we have something we call, so the cell process will go through a cell respiration, okay, aerobic. Okay, so let's see, cellular respiration, three main phases. What are they? We have glycolysis, okay, that's a splitting of glucose into pyruvate. And we have what? Followed by something we call Krebs cycle. Okay, then followed by electron transport, okay, chain, like that. Okay, so these are the three main stages of what? Of cellular respiration. Now, what happens is that when you add this substance, the potassium cyanide, okay, like that. If you add the potassium cyanide, okay, potassium cyanide to where? What the potassium cyanide does is that it can stop the activities of what? Honestly, the vast majority of energy produced. So these are the steps. Each of them, energy will be produced in the form of ATP. Each step, energy is produced in the form of ATP. But the vast majority of energy produced is from what? From the electron transport chain. Okay, from the electron transport chain. So from the electron transport chain, that we are going to get what? A lot of energy produced from here. Okay, so vast majority of what? ATP will be produced from the electron transport chain. Vast majority of the ATP will be produced from the what? The electron transport chain. All right, and this electron transport chain, with this vast majority of it, is produced from the electron transport chain. Okay, what is going to happen is that when you apply cyanide actually stop the activities of this electron transport chain, so that ATP is not what? So that is the reason why cyanide is a very toxic substance to human body. Okay, it's very toxic substance to animals. Okay, it's a toxin because when it gets into our cells, they can stop the cellular process at the electron transport chain. They can inhibit the process, so the ATP will not be produced. Okay, so now let's come here. So what this one is saying here is that, okay, water absorption, okay, so that when you apply respiratory inhibitors, such as what? Potassium cyanide, okay, it will reduce the rate of absorption, okay. Why is it going to reduce the rate of absorption? Because it is believed that once you inhibit respiration, there is no work, there is no energy available, there is no ATP available. So that's the argument. Once you inhibit respiration, there is no ATP available for what? For the cell to use. Okay, once respiration is what? Is inhibited. Okay, so when you apply something like the potassium cyanide, and we know the potassium cyanide is going to inhibit the what? It's going to inhibit the specifically the what? The electron transport chain. All right, so the ATP can be produced. Now, so here some ATP will be produced here, some another ATP will be produced here, but the vast majority, okay, over 20 something ATP will be produced here. Like the net ATP is just 2, here 2. Okay, so the vast majority will be produced by the electron transport chain. All right, but this is the situation that, okay, this is the situation that if applied what? If apply potassium cyanide, and this potassium cyanide is going to stop that the electron transport chain, okay, and when that process is stopped, what is going to happen is this. It means that there won't be enough ATP available to what? For water absorption. So that the argument is that when you apply respiratory inhibitors like this, like potassium cyanide, rate of water absorption is reduced, okay, because there is what? The amount of ATP available to power water absorption has reduced what? Drastically. Okay, all right. So we have what saying the exudation. So which means he's saying that when you apply, rate of water absorption and the exudation from cut stem all reduce. So what he's just saying here is that when I apply this potassium cyanide, whereby I stop the ATP from producing from I stop the ATP production, the energy that is required to power the well. If I stop it, then it means that even when I cut the stem, okay, even when I cut the stem like this, when I cut, the amount of water that will come here will not be much. The exudates, okay, the exudates that will come out of the stem, cut stem, will not be all that much. Okay, when the potassium potassium cyanide is applied to the root, which means when I apply potassium cyanide to the root and I cut the stem, okay, I'm not going to get enough of what? I'm not going to get enough of the exudates or water coming out of the well. The absorption from the cell and enough of, even when I cut the stem, even the exudate that will come will reduce because I've used what? Respiratory inhibitor to stop the process, the energy reduction. And then the last one is that water absorption is also influenced by what? Plant hormones. Okay, so there's plant hormone called auxin. Okay, so water absorption is also influenced by what? Plant hormones. So they brought 3 theories under the one. Under that, they are saying that water absorption is by active process. Okay, all right. But if it is active process, the active process, what they are saying, they say that the active process, it will occur, but it has nothing to do with osmosis. That's what these 2 people are saying. These 2 people are saying that, okay, that that's the Kramer and the Tierman. Okay, they are saying that yes, it is by active process. It has nothing to do with osmosis. Okay, and for that matter, okay, the evidence is that roots of plants, even in flooded area, will still wilt if there's no much air in the soil. Okay, and also when you apply respiratory inhibitors to plant roots, rate of water absorption also reduces. And then the final point they made is that water absorption is influenced by what? Plant hormones, such as what? Auxins. That anytime there is low concentration of what? There's low concentration of what? Of auxins, okay? Increases what? Water uptake, okay? So water absorption is influenced by what? Plant hormone. And to extend that when anytime the auxins are of low concentration, okay? Auxins of low concentration here, okay? Low concentration, then what? There is uptake, increase in what? Uptake of water, and then the exudation. All right. So that is what they are saying. Okay. So these are the evidence. Wilting of fruits, even in flooded area where the soil is not well aerated, and then on top of that, application of respiratory inhibitors, okay, to the root reduces water absorption and stem exudation, and then water absorption is influenced by what? By plant hormones such as auxin. That as the auxin concentration increases, water uptake and what? Water the exudation tends to what? As they decrease in concentration, the water absorption and exudation tend to increase rather. All right. So these are aspects of what? Of the theory. So let's do a quick recap of that. Okay. So we have what? So we have various schools of thought that are saying that osmosis, there are two mechanisms of what? Of water absorption. We have the what? We have the active absorption and passive absorption. Okay, so various theories have. So let's see the active absorption. Under the active absorption, there are two things we talk about. What are they? Under the active, we have the osmotic theory, and then we have the non-osmotic theory. The osmotic theory presented by Atkin and White and Priestley. Okay, they said that. Okay, they said that water will be absorbed as a result of what? Water soil sap gradient, and then water will move from what? The region of what? Of high concentration of water to low concentration of water. And he supported his claim with what? With pressure. All right. But the counter of that is that if water should go by osmotic mechanism only, then the question is that how will the what? If water should go by osmotic mechanism only, then how will water move between what? How will the water move between the cells of the cortex, which tend to have what? Comparative, which tend to have comparative what? Comparative this thing, concentration. Okay, we tend to have comparative concentration. All right, we tend to have comparative concentration. How would the water move from here to here? You get my point, right? So we tend to have comparative. And another point is that if water is also moving by osmotic process, osmosis requires semi-permeable membrane. But this is a situation that the trachea, which is the one of the key components of the xylem, is made up of parenchymal cells. And parenchymal cells are dead cells at maturity. So how would the dead cell act as what? Semi-permeable membrane? That's impossible. So these are the counter to that. Then we have the still under the active absorption process. We have the other group, Kramer, okay, Kramer and then Timmer, saying that, oh no, there is active process that has nothing to do with what? Osmosis, okay, and even to extend that water can even move against diffusion pressure gradient, and they are saying that water absorption requires what? Energy in the form of ATP from the plant root cells, okay, and their argument is that yes, if in soil where the soil is not well aerated, even in flooded soil, the roots can wilt even in flooded soil, okay, where the soil is not aerated, okay. So if it doesn't require energy, why is the roots wilting? Okay, so that's the argument, because they are saying that there's no oxygen in the soil to generate what? To carry out the cellular respiration to generate energy in the form of ATP. And they also buttress their point is that if the root cells are treated with what? Are treated with respiratory inhibitors, then absorption of what? Absorption of water, and then even exudation from a cut stem, the two of them are going to reduce with the motive that, with the argument that if we inhibit respiration, it means that there's no much energy to drive the water. Okay, and then the last point is that water absorption is also influenced by plant hormones such as what? Auxins. Okay, to extend that when there is low concentration of auxins, okay, in the plant, the water uptake and what? Exudation tend to what? Increase. Okay, all right. So that is for the active mechanism. Now let's go to the passive mechanism. And when it comes to the passive mechanism, what happens is this. So the passive mechanism goes this way. The passive mechanism is the one that we actually know. Okay, so this will explain the forces responsible for these are saying that. Okay, this explain the forces responsible for absorption of water into the root. Okay, all right. So this theory explains that the forces responsible for what? Absorption of water into the root are governed by other cells. Okay, so what this one is saying here is that yes, what will drive the force? What will is not necessarily the root hair that is generating those forces, but sometimes forces from somewhere else is what is doing the magic. Okay, so there's this adage that there's this analogy I've forgotten. It's came into my mind that I could have been. Okay, so what they are saying that yes, the forces, okay, that will actually absorb the water is not coming from that will drive the absorption of water by the root. It's not really coming from the cells of the well, the cells of the root, but they are coming from other parts of the plant. That's the argument. Okay, so let's see what are they saying. So to them, yes, it is passive process. If it is passive process, what if you are saying it's passive process, then it means that it does not require energy. Okay, it does not what? It does not require energy from the cell, from the root cells. The roots from the root cells, right? Okay, it does not require energy from the what? From the root cells. All right, from the root cells. Then, if it doesn't require the energy from the root cell, then how would the absorption take place? So the governing force to them, the governing force is rather transpiration in the shoot. Okay, so what to them? Let me click this one here. So to them here, let me go and draw here. Okay, to them here, this is the plant. This is my plant here. The cells are here, the root cells are here, like here. So they need to transport, they need to absorb the water here to the roots. Okay, so let's say these are the root hair cells there. All right, they need to absorb it to the xylem, and the xylem will send it up. So to them, so let's say this is the leaves here, the leaves here, the leaves are the top 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 here. So to them, what they are saying here is that there's something we call transpirational pool. So transpirational pool is water is being lost from here, from the leaves here. Okay, as water is being lost from the leaves here, then this water being lost, it creates some sort of tension, and that's what draws the water from the soil up. Are you with me? Okay, so to them, transpiration is occurring in the leaf. And as transpiration occurs in the leaves, it creates some sort of tension in the leaves. And this tension will cause water to be drawn from the what? From the soil all the way up. Okay? So the force that is really absorbing the water is not really coming from the what? From the roots. Okay, there's no ATP being broken down here, but rather as water is being lost from the leaves of the plant, it creates that sort of what? Tension. Okay, it creates that sort of tension, and that draws the water from the soil up. Are you there?
Yes.
Are you there?
Yes.
Okay, so my question is this. Of these two things that I have described, okay, so you see, so the passive absorption theory, is saying, oh no, you know what? Two of you, those of you are just saying active process. Even some are saying that Kramer and his people are saying that, oh, it is by non-osmotic. Okay, the other people, the first group of people, okay, they are saying that it is by Priestley and his colleague Atkin. Okay, they are saying it is what? Osmotic process. And this one, then the active people came and said, oh, no. Give us a break. You know what? Actually, it is passive process. It is passive process, but this passive process, the force that is actually driving the thing is not coming from the root. So it is passive. But if it's coming from the root, then it is active process. So the force is not coming from you. Okay, so somebody is paying for it. Do you understand that? So somebody is just taking care of it. So let's take it this way, that Ajiman's wife, okay, is looking beautiful. She's driving a nice car, okay. And when you see it, Ajiman's wife is working, okay. So people are saying that, oh, this is actively, it's an active process. Active process in the sense that the lady is working, and for that matter, she's making her own money, and her own money is what she's using it to take care of herself, and blah, 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 blah. But in reality, that's not the case. But rather, what is making that lady beautiful, that nice car she's driving, is because Ajiman is taking very good care of her. Okay? So if the energy were to come from the lady, those energies were coming from the lady, then that would be active absorption process. Those theories that Atkin and Priestley and Co, they were saying will hold. But there's a situation that no, the passive theory is saying that give us a break. Okay, the passive absorption mechanism. He said, no, give us a break. Okay, actually, the lady there you see riding that beautiful car there, that car was bought by his husband. It was bought by Ajiman. You understand? So the force is not coming. The force is not coming from the plant root directly, but it is coming from an external source. What is actually governing the absorption of water is coming from the external source. Okay, so we have the active, the active absorption, which was proposed by the word. By even the active absorption, we have two parts of it, which is the osmotic theory and the non-osmotic theory. And then we come to the passive absorption. Passive absorption, no, the energy is not coming from the root cells. No, not at all. But there's something that is happening in the shoot, the leaves up there. Okay, it's something that's happening here. That the leaves here, they are doing what? They are taking water. Water is being lost from the leaf of the plant through the stomata, through the cuticle, and stuff like that. There's lost through the back of the stem, through the lenticel. Okay, water is being lost through the what? Through the stomata of the leaves, through the what? The cuticle, okay, and through the what? Lenticel, okay, of the stem. Okay, this one, the lenticel is at the back of the stem, like that. So there's water loss, and that water loss creates that tension, and it is that tension that's what that actually creates the what? Diffusion pressure deficit. Okay, so there's this diffusion pressure deficit in the leaves, and that deficient pressure deficit in the leaf will create that stream. So eventually, you will pull water from it, just like we are passing book. Okay, so Ajiman is wife. So now let's take it this way down. So let's take Ajiman here. Let's look at how that thing is going to work. So Ajiman works and gets the money from the government. Okay, so let's say Ajiman is here. Ajiman works, get the money from the government. All right. Okay, so let's take Ajiman is the leaves here. Okay, Ajiman is the leaves here. All right, and the wife is a stem here. Okay. Oh no, let's put this way. Let make it this way. So let's take it this way. Let's take it this way that the money is being pulled from the children are pulling the money. Okay, so let's take the children to be the leaves here. The children are the leaves here. Okay, and then the lady is a stem. Okay, here. All right, and then Ajiman is taking the, no, let's take it, let's see. They are pulling from here. All right, let's see. So water is coming. Okay, let's see. All right, so let's say the children are the roots here. So the children are here. So what is going to happen is that, okay, so let's say the children are the roots. The lady is a stem, and then Ajiman is the leaves. So you see the water is being pulled from the leaves here, and as they pull it here, the leaves will pull the water from the what? From the stem up, and the tension created in the stem will also pull the water from the roots. Okay, so the water is being lost from here, from the leaf up here. All right, and this will create tension here. It will cause water to be pulled here. Okay, so if I use the water as money, if let's say I use water as money, that one, the children will be the leaves here. Children need to buy stuff, they need to eat, they need to survive, they need to buy clothes, they need to survive everything. So the children are the leaves, the stem, the wife, and then the roots is here. And so what is going to happen? So let's say the government is the soil where the water is. So what will happen is that the children will take the money, okay, will pull the money from here. Okay, they need their daily survival and upkeep and stuff like that. Is what is pulling them. That's the transpiration. Okay, pulling the water from them, pulling the water from them here. Okay, that's pulling the water from them here. And as they pull it, the next thing, I'm hungry, I am that, I need this, I need that. They'll go to mommy. Okay, they'll go to mommy, and mommy will give them here. And as they do that, remember, they'll do what? As they go and spend the money, as the children go to school, they pay school fees, they buy books, they do that. So the money will go. When they go, they spend it. So it will create deficit. The money you give them today for food, for water, for everything will go. So they will go and spend it. That will create the diffusion pressure deficit here. And that diffusion pressure deficit will cause the next day they need to get money from mommy. So they will pull mommy here like that. Okay? They will pull mommy. They are not going to spare mommy. Okay, so they will do what? They will come and pull mommy like that again. Mommy, I need money. Again for school, again like that. And as they pull mommy like that, okay, so pressure deficit has been created here, pulling in it from mommy. Then, as they pull it from mommy and mommy gives to them, pressure deficit will be created, diffusion pressure deficit will be created here. Okay, deficit will be created between the stem and the root. And then the next moment, mommy is where? Mommy is also pulling, okay, pulling daddy like that. Okay, pulling daddy like that. Pulling daddy this way like that. Okay, pulling daddy like that. And then as they pull daddy this way, now that daddy will also take the money from where? Now daddy will also take the money from where? From the government. Okay, so the government will also give the supply. Okay, so daddy absorbs that money from the what? From the soil like that. So let's say the soil is the government here. Okay, and as the word, as the mommy who is the stem of the house connecting the children, and then the word daddy. Okay, as they pull you, as the Ajman is the root here, so Ajman will take the word, the money from the government through his work. The mommy will take the money from him. Mommy will give the money to the kids. The kids will go and spend it like that. So this is what we call here transpirational stream. So according to this theory, what this theory is saying here is that no. Okay, honestly, the force for what? For absorption is not actually coming from the root, but it's coming from the shoot. Okay, created by the what? Created by the transpirational pool from the shoot. And the transpiration is the what? Loss of water from the what? From the plant, either through the stomata, through the cuticle, or through the lenticel of the stem. And as the water is being lost from the top here, then there's what? Then it will create some sort of tension. So I pull you, you pull me, children pull mommy, mommy will pull daddy, and daddy will pull government. Okay, so then the cycle continues. All right, so this is what the passive mechanism is saying. Okay, so water, this and that. So in your opinion, which of them do you sound very plausible? Yes, the passive and then the active. In your opinion, which one do you think? In your opinion, yes, anybody from the audience, please. Please. Yes, anybody. I think I think both will still work to some extent, because you see that some parts, yes, energy will play some part. Some part, the root pressure will also be there, because when you cut plant, you see that still the exudates, okay, will still cut, because if plant absorption, okay, from the soil is solely by transpirational pool, like it means that when I cut plant, when I cut the stem, then there shouldn't be any water coming out of the stem. If it is solely by transpirational pool, then when I cut the plant, there shouldn't be any water coming out of the stem, but root pressure is there. So which means that both mechanisms, they all work together to some extent. Okay, but the transpirational pool of this one is the principal mechanism. Okay, the root pressure will contribute, no two ways about that, but the transpirational pool is the what? Is the principal mechanism. Okay, whereby the deficit will be caused by the what? As water will move from what? The quarters from cell to cell, because transpirational pool has been created. Okay, transpirational pool has been created here. Okay, so water, as you draw the water from me, I draw the water from you, you also draw. So the cycle goes on and on and on and on and on. Everybody is pulling somebody. Okay, so you take it from me, I take it from somebody, and the person take it from me, to go on and on and on. So yes, transpirational stream, this transpirational pool, as water is being lost from the leaves or from the stem as a result of transpiration, the tension will be created, water will be drawn so water will move from quarters to quarters, and then eventually it will also cause the water to be drawn from the roots. Okay, all right. So both active and then the passive mechanism, they all work together. Okay, all right. So the tension interacts with it. Okay, comparatively low in other root cells, put the roots in what? In tension. You understand? So as water is being lost from the top part of the water, as the water is being lost from here, it creates tension there, because if there's no water there, it means that the solutes there will be more concentrated. And if more concentrated means that it will create what? High osmotic pressure. Okay, and high osmotic pressure will create what? Will remember the diffusion pressure deficit depends on what? or osmotic pressure. If there's high osmotic pressure, the diffusion water, the diffusion pressure deficit will also increase. Okay, and it will pull more water. So it's like you pull me, I pull you mechanism. So in that case, this one will pull. So let's say the cells are here like that. Cells are here like that. Okay, let's say cells are here like that. As the one in this one is being pulled, becoming dry, it will pull the one in the stem here. Okay, and this one you pull the one here. So you pull me, I pull you. I create tension. You create tension. The next one, you pull me, I pull you. You pull me, I pull you. So it goes like that. So that's the mechanism. So the cortex. So here, as they are being pulled on the side here, you pull the water. I pull the water here. This one is pulled up. When it pulls up, diffusion pressure deficit will be created here. Then this one will pull you. And you also pull the one here. So it is all about you pull me, I pull you. It goes on and on and on. And that is what established what we call the mass flow against diffusion. Okay, so that's the word. So you push me, you pull the water, I'm pulling you. Okay, like that. So that's that tension. Okay, that is what is drawing the water as a result of what? Transpiration pool. All right, in the leaves. All right, as the water is being lost there. Okay, all right. So let's see the difference between the active, which means that both mechanisms tend to occur. The active absorption occurs as well as the passive absorption. So what is the difference? So active absorption occurs in the root hair, okay, in the root. Okay, passive absorption occurs in the shoot and then the leaves. Okay, so the shoot part, the upper part of the plant. So the two mechanisms all occur. So active here, okay, the active mechanism, okay, occur in the roots and then the root hairs. Okay, so we need some energy to drive things. Okay, that one, okay, that's true. And then the passive one occurs in the shoot, the upper part of the plant, the stem and then the leaves. And then the active one occurs through by two mechanisms, either by osmotic or non-osmotic process. Remember the osmotic theory was suggested by the Priestley and then the Atkin. And then the non-osmotic are the Herman and then the Kramer. Okay, and then so that they occur by by osmotic and non-osmotic. And then the passive one is due to active transpiration in the area parts of the upper parts of the plant. Okay, and here the roots hair tend to have high diffusion pressure deficit compared to the cell, thereby pulling the water molecules in, while the absorption of the passive mechanism is due to the tension created by the transpirational pool. The tension created by the transpirational pool. Okay, so these are the three main the mechanisms of so both passive and active transport mechanisms, okay, are involved in in absorption of water. Okay, at the basic level, we always tell students that absorption of water is solely by by osmosis. But you realize that there are two things that come. I think we talk about the passive process as well, but we don't mention the passive process. Okay, we have the passive process. The passive process is through the transpirational pool. That through the loss of water in the leaves and then the stem, creating some sort of tension, which actually draws water from the nearby cells. So you draw from me, I draw from you, you draw from me, I draw from you, and all the way up. Okay, all right. Okay, so you have next class, so maybe a quick one here, and then so let's see external factors quickly, and then so that you can join your class quickly. Okay, get a little bit of breaking join. So here, what are some of the external factors that can affect water absorption. Okay, the external factors that can affect water absorption, availability of water in the soil. Of course, if you have more water there, if there's water in the soil, that actually influences what? Absorption of what? Of water. If you have water in the soil, that's what influences absorption of water. And the soil temperature. Okay, so we've realized that research has shown that between 20 to 30 degrees Celsius, okay, it's actually suitable for water absorption. Okay, when the temperature is too high, when the temperature is too low, water absorption is being hampered. And then soil aeration. Remember, we talked about the active process. Okay, we talked about active process, whereby even in what when we need there should be enough oxygen in the soil. Okay, for what? For cellular what? For cellular respiration. Okay, respiration, for cellular respiration. Okay, so we have what? We have availability of water, concentration of what? Soil solution. Okay, the what? Soil temperature and soil aeration. That's the, okay, you having the oxygen in there for what? Oxygen in there for cellular respiration. So these are some of the external factors. Now let's see some of the internal factors that can affect water absorption. Okay. Now when you talk of water absorption, please don't confuse yourself with water going uphill. Water absorption is basically water moving from the soil all the way to the moving from the roots of the soil all the way to the xylem. That's what we call water absorption. Water moving up is different. But the passive mechanism is whereby the tension is what causes the water to be drawn. It creates something like transpirational pool. Okay, that's what it's saying. Okay, but when you talk of water absorption, it's basically water moving from here to here, moving from the what? From the base here like that, from that horizontal movement of water like that, from the soil all the way into the xylem of the root. That is where we talk of water absorption. Water coming from the soil into the xylem of the roots. Okay, that's the water absorption. Okay, all right. And then, so what are some of the intrinsic factors? Okay, so internal factors of the plant. We are talking about transpiration, which I've just given a head start, and then the absorption root system. Okay, so absorption root system. All right, absorption root system. Absorption root system, and then the metabolism. Okay, so as we said earlier on, if there are some sort of what, if there's no respiration going on, so transpiration, now we know the transpiration, which ensures the what, the passive process, that's a passive absorption process, Then we have what, we have the absorption, absorbing root system, the absorbing what, root system. Okay, so we remember that whether we have the tap roots or the fibrous roots, or how spread the root systems are on the surface of the soil. Okay, and metabolism here we're talking about what? Respiration, those cellular respiration. Okay, respiration. All right, respiration that will generate some sort of what, energy. All right, so as we said earlier on, that when we have what, the potassium cyanide. Why? Because the cyanide tends to what? Inhibits what? Electron transport chain. Okay, electron transport chain. Okay, all right, good. So metabolism, absorbing root systems, and then the what? And then the transpiration. All these factors tend to affect the rate of what? Water absorption. Okay, all right, maybe 2 more minutes and then maybe we can call it a day. So the next thing that maybe I'll just talk about briefly is what? Is the fact that we have what? We have something we call what? Ascent of sap. So ascent of sap is basically talking about water now let's take it. Let me draw again. Okay. Oh, look at me. Let me draw here. Let me draw again here. So now let's take it this way, that you have what? So this is the plants there. This is the plants there. This is the root system here. This is the root. All right. The root is here like this. Okay. So this is the xylem. Let's say the xylem is here. All right. It's like that. So what the absorption going to happen? What is going to happen is that water is moving from where? Water moving from here all the way here. Okay, this horizontal movement of water here, like all the way to the xylem. This is the absorption. That's the water. Okay, water what? Water absorption. Okay, absorption. That's the water absorption. All right. Now the next one is water moving up here like this. Okay. So the next one is, now I want the water to move up. So water moving this way like that. Water moving like this. Okay. Water moving. Okay. Water moving this way. This way. Water like this is absorption to the xylem. Absorption. Now the water is in the xylem. How does it go up here all the way into there? So, okay, we know the what, we know the mechanisms, we know transpiration will be there, we know root pressure will assist a little bit, and then other physical forces. Okay, all right. So then next time when we meet, okay, so here we have the word. So we'll talk about the word. So the next time when we meet, okay, we'll talk about root absorption of water. So the next time when we meet, we are going to talk about what? We are going to talk about how the water is going to, as the water gets here, how does it go up here? Like that. Okay? All right. So that's what we're going to tell you. We'll talk about three main mechanisms. We have the what? We have the transpiration, we have the root pressure, and other physical forces. That's basically what we're going to talk about. Okay, so ascent of what? Of sap. Okay, that's the water moving up here like this. Okay, all right, great. So we'll end the class here so that you can prepare for your next class. Okay, and then so that God willing, I will. But in fact, we are slightly behind. So one of these days, okay, I will speak to Ajiman so that we could have some. Let me finish my quizzes within next week, and then we'll try and fix some time so that I can also give you some. I need to fix some time so that I can even give you some trial questions as well to also play with. Okay. All right. Thank you very much for having me. Thanks for coming to the class. Okay. So God willing, I'll meet you next week. Okay. All right. Thank you. And then I couldn't give the out.
Thank you, Doc.
I couldn't give the shout out, but I do see you all. I see all my ladies. Okay, Henrietta, I see you. Okay, I see all my ladies. Please, I see you, and I appreciate the fact that you made it to class. Okay, I see you all. Okay, I see my allergies, the allergies that who celebrated the solar. Julina, I see you. Nico, I see you. Okay, David, I see you. Ebenezer, I see you. Hey, Tidani.
Thank you, Doc.
One Beatrice. Oh, Sissy, Cecilia, Anna, I see you all. Thank you very much for making it to class. Okay, Ernesto. Oh, Fidelia, one Gifty. Oh, Ken Afi, Muhammad Afi. Okay, Josephine, I see you. Oh, my Juliana, Anita, one Anita. I see you all. All right. Flomina, I see you. Okay. Rosamond, today you're very early in class. I see you. Isaac. Oh, Kiniko. Hey, Kiniko, today you're down two bad boys. You're taking over from Ajaman. Oh, Belinda, I see you. And Belinda, I see you. Lord the Kingsley. Lord the Kingsley. Ernesto. Oh, Imana Ponsa. Hey, King the Bashir. I see you. Anthony. Oh, Eben, I see you.
Please, Doc, may God bless you so much.
Yeah, Charlie, thanks for coming. Thanks for coming to class. Thank you very much. Okay, I really appreciate you. Well done.
Thank you, Dr.
Right. Okay, so Belinda. Oh, Belinda. Oh, Salamatu. Salamatu. I'm still waiting for my car. Salah, I'm still waiting. You and Bashiru and Tijani. I'm still waiting for the car. The Eid al-Adha, the Eid al-Fitr. I see you. Kofi Yabua. Yes, I see you. Oh, one Valencia. Valencia. Oh, Valencia, give me a wave. I see you. Give me a wave. Tijani.
Yes.
Tijani. How many times have I called you? Tijani.
Once.
And you say, oh, why you sick? Why you sick? Why you sick? Why you sick? Oh, Charlie, why you sick? Charlie, what's up? Charlie, everything cool?
Everything is good.
Oh, we thank God. We thank God. Charlie, they glad there. Charlie, Edgeman Bowa. He said, Charlie, when you say you will see something, but you don't see anything from your side. Me myself, who all talk, say, Charlie, at the word you see Titani and Salamatu do the action. Okay, you didn't say anything. Okay, but when you come, you didn't say Edgeman Bowa. Edgeman,
You will not come here again.
Charlie, oh, you see,
Bad boy,
He can't come here again.
because you're a bad man, that's why all this thing they are scared. But they have to say maybe Nadia Kende to bring the egg ladder. But when Nadia Kende comes to Adjuman's house, she may end up becoming a root pressure or something. Translational stream may occur. So that is why you see when Tijani didn't send the head ladder. So it's all your fault. It's all your fault. You have caused all the problem. Okay. All right. So I wish you all the best and have the best of the day. Please have fun and enjoy your class. Please.
Okay.
Thank you very much. Please, dog, we need a slide too.
This one, the one that we just did. Okay,
yes,
I will. All right. Okay, so then I will do this. Sure, I will do that. Let me do this thing. You need all with all the scratches on this. I should keep all the scratches.
Yes, please.
Okay,
yes,
all right.
please.
Okay, so,
yes, dog.
Okay. So let me do that now. I'll send it to Agreement pretty soon. Okay. All right. Thank you.
You see, Ajman is now joining again. Bad boy, he ran away and he's not joining.
And now you are joining again.
Ajman, you're all scared of him. I know that.
Bad boy, Ajman.
Ajman, such a bad man. Because of you, the head ladder, we couldn't send her here to bring the things.
Ajman is a Dakwala.
So my city place where you be
I have
play like that.
no problem.
Otherwise, you see your life. Because of you, you are the seller or you not get a seller. Okay? Go no get a seller. Okay, so let me remove this part. So this way we'll do it next week. So let me save this one for you. Okay. All right. So let me send this one quickly. I don't know whether if I send it, whether it will come. I doubt. I doubt. So let me send it back in straight up. Okay. Right. So let me end the letter so that I can send it back in.
Please, dog. Please, dog.
Other class.
Okay, don't worry.